Thank you, Jussi. All right. So also a warm welcome on my behalf. I think that the topic that we're discussing today is one of the most exciting ones at the moment. And of course, I do have a background from a very long time ago also in some of the topics that are being discussed here, but I have to confess that, especially looking at the audience here at the Micronova, that I haven't been this nervous about making a mistake in a long time. So I already try to kind of like preempt your kind of like looks. I'm most likely going to say something stupid about quantum mechanics here. So just to kind of like reset everybody's expectations. But considering that there are far more knowledgeable people coming to talk, I'll try to keep this at a sort of a layman's level, but let's see if I succeed. But I also wanted to start first with a sort of a personal note, and kind of like then that why I think that there is sort of kind of like that we are at the brink of something really big at the moment. And the thing here on the left, probably nobody has seen this, but it's an IBM 5100. It actually is a computer before the IBM PC from the 70s, and that's also not this example here, but that's the first classical computer that I have ever used. My high school had one. So this is where I started using classical computers and kind of like found a completely new world. Then the thing here on the right is IBM Q, their quantum computer, which is actually accessible through the web at the moment already, and that's the first quantum computer that I have used. I don't know if it has been this example exactly, but it's kind of like then that I've been able to run a small program there. So in a sense then that kind of like that, and I think that there are sort of the same kind, I have the same kind of feeling then that a whole new world is about to open up at the moment, and it was really simple stuff still in 1980 when I first laid my fingers on this one. I think that it's even more earlier days at the moment with the quantum computers, but something big is brewing. This comes back then to this thing that kind of like that how hard some things are to understand, and sort of then that I have studied quantum mechanics, and I thought I understood something back then. As I grow wiser and older, I start realizing that how little I have understood in the past and how even less I understand now. But it's sort of kind of like then that I don't know if it's readable here, but it's kind of like x-axis is that how many years of math is needed to understand. So many is here, a little here. And then how philosophically exciting the questions are to a novice student, very at the top here. And quantum mechanics is definitely in the sort of if you pardon my French, in the weird shit category, that it is really at times totally counterintuitive, and it's sort of in the classical world where we live, it's hard to understand some of the concepts that are there. But it's also then that those concepts are the ones that make it so exciting and also kind of like open up these possibilities that we discussed today. Why is it then sort of then that if you think from the sort of the business point of view and kind of like then that okay, I don't care how the computers work, why should I care about quantum computing or any of these things? Most people, at least in the business, have heard about Moore's law, which is basically saying then that how kind of like then that we've been basically on an exponential curve, that how computing power has been increasing. This is already a bit old graph, but it's sort of still that we have been on this absolutely amazing path with classical computing. This is a logarithmic scale here even. So in a sense then that kind of like that we've been enjoying great productivity increases, great innovations, these kinds of things based on that what is coming out of the transistor. And now we are reaching that era that soon the Moore's law development is going to fall off the cliff, or basically plateau, so that that laws of physics are starting to interfere with this one. So then we need something new to come and replace, whether it's optical computing, quantum computing, DNA computing. Human brain is still in many ways totally superior in certain types of tasks and energy efficiency. So, but the basic point why we should be, if you're a total layman, that why you should be interested in quantum computing is that we need something here. We don't have the solutions. And it's also sort of then good to understand that this curve has been continuing even at the time that when we had mechanical calculators. So then we got the transistor, first the tubes and then the transistors and microchips. So there have been completely new technologies that have come over the past. So in the same sense, we can be optimistic that we can keep on continuing this type of exponential increase then with new technologies. Today we talk about quantum computing, and it's actually a fairly, on one sense, it might feel like an old idea. On one sense, it's fairly new. So my personal hero, Richard Feynman, in the early 80s, basically came up with the idea then that, hey, you could actually start, when you're trying to calculate with classical computers, transistor-based computers, then that how nature systems work, quantum mechanical systems work, actually you could use a quantum system to calculate that instead of using a classical computer. So that early 80s is when it started. So in that sense then that we're talking about the phenomenon that's still less than 40 years old. But on the other hand, it says then that kind of like that how long certain things develop, because we are still at an early stage before we can really realize this in a practical sense. So why is it so different then? And for some of you here, this is now basic stuff, and this is probably the place where I make now the horrible mistakes on quantum mechanics. So try to suppress your laughs. But in terms of kind of like that, what's the difference between a classical computer and a quantum computer? Classical computers are the bit-based, so it's all zeros and ones, and it's all sort of, you could say that it's deterministic. If the computer works correctly, it will always calculate the same result. Quantum mechanics is by nature, you could say, probabilistic. So in a sense then that it gives you, actually you need to run the calculation many times and you get the probability distribution. Not a single right answer, but you get the distribution of different answers. Second thing is then that it's not about zeros and ones, it's about states and superposition of states that you have basically a probability distribution that it can be either in an up state or down state or 0 and 1 state or some combination of those. And also then the really weird thing which is around entanglement, that two states can be connected even over distances. So this is the spooky action at the distance that Einstein was talking about. And in a sense then that why can then classical computers do so many things has been then that we have learned how to program, then how to manipulate the bits in a way then that we can do one calculation, then the next one on the same result, and next one. So it's basically repeating many calculations in a really rapid fashion, and as the classical processors have become faster and faster, and with more and more transistors, we can do more and more calculations at the same time. And that way we have been able to kind of like do amazing things, with computers. Now, in the quantum computing world, we essentially start calculating then with all the states at the same time. And in a way, what it enables is that we can of course, we still need to do things in a serial fashion, but we actually can come then to the right answer in a system in a you could say parallel fashion. And the advantage that we can get with quantum computers can be just amazingly big in certain applications. And I'm sure that we don't know yet all the different possibilities here, but at least already we know that there are certain types of algorithms and problems that can be solved on a quantum computer in a fashion that it's several tens of orders of magnitude faster potentially. And for example, this, if I just pick a simple thing here, factoring, which is required essentially then for cryptography or breaking secret messages or sort of decrypting them. In classical computing, the complexity grows exponentially. 2 to the power of n, meaning then that the size of your you could say the encryption key increases, the complexity increases exponentially. And when you start talking about n 2000 versus then this number is absolutely gigantic. Whereas in computing, quantum computing, the growth is actually what's called polynomial. So in a sense then that when n is large, this can be tens of orders of magnitude smaller. And that's a gigantic difference. So in a sense that you could say then that the difference is that you can calculate with a computer something in a finite amount of time versus then the whole time that the universe has existed on a classical computer. Now, of course, the target is that we create a universal quantum computer that anything you want to do, you can just punch it in there. At the moment, and I'm sure Mikko Möttönen from Aalto and VTT coming up next will talk more about this. So that we are not quite there yet, but it's also sort of then that we can, before we build the universal quantum computer, we can start simulating how molecules work. So we can have lots of applications around, for example, designing new materials or designing ways how to make certain materials in a more energy efficient way, simulating physics, also around doing certain type of math much better. And it happens to be then that one type of math around linear algebra, which can be done very efficiently, hopefully with quantum systems, is actually very relevant for artificial intelligence. So it might be then that the real breakthrough in AI happens also when we start be able to do it on quantum systems instead of normal classical computers. When we talk about AI, we many times talk about that kind of like that AI is coming, and then people come and remind then that, hey, we've been using artificial intelligence and machine learning and those types of things already for quite a long time. I feel obliged also to remind everybody the same thing about quantum technology, that we have been using technology that utilizes quantum mechanics and quantum effects already for quite a long time. So we wouldn't be doing any GPS positioning or basically any kind of communication without lasers and quantum and many other types of solutions as well. So in that sense, of course, it is already very much part of our daily living, but this is still kind of like the early days. This is the 1.0, and the 2.0 is just coming. Then a little bit about the sort of the industrial politics here. I've been going around in Europe quite a lot, and we've been talking with Christina Andersson, who's also in the EU committees, and many other people here. That of course, this area has been on the agenda for some time, and these numbers are from 2015, and this is kind of like highlighting with the size of the bubble that how much different countries and EU are investing into quantum technologies. But what's not visible here is the rate of new investment going in here. So for example, Germany is here at 120 million euros in 2015. Now they have a program that's worth 600 million euros. China, 220 million euros here. They just recently announced a program where they will spend more than $40 billion on quantum technologies. Same type of increases in US and elsewhere. So in a sense then that what we also with this seminar today want to do is then to start raising the awareness in Finland beyond just the research circles then that this is not sci-fi. So this is not that kind of like then that we want to be living in some sci-fi book and kind of like talk about things that will be relevant in few decades. There's a heavy investment going in Europe on this. There's the quantum flagship program, whereas also sort of, for example, VTT and Aalto are part, and some companies. But this is now really kind of like picking up steam in the global scale, and China's investment shows then the level of commitment around these technologies. And in that sense then that I think that the Finland has to also start waking up then to this now. And we had the now for 2 years there's been this big effort around kind of like doing the Finnish AI strategy, and what we are now today suggesting is then that we need also the Finnish quantum strategy, and now is the time to start thinking about also this in an industrial scale and how to get companies excited about this thing, but also sort of make sure then that with the of course we don't have 40 billion euros to put into this thing, but still with the small investments that we can grab our share and put have a stake in this business. Because in few years time, and it may be a little bit longer than just a couple of years, but still in few years time, a lot of value creation in the society and industry will be done through quantum technologies, and Finland has to be on that curve. So I hope that everybody gets excited about this area, but also then that you take that excitement further than just this room and kind of like the small group of true believers that exist in the research area, and kind of like then that we can make this into one cornerstone of Finnish industry also in the future. Thank you.